Okay, hey, it's HESSEL again. This time we have our A plus physics worksheet, Kinematics, horizontal kinematics. So here is the worksheet. Here's page 1. Numbers 1 through 5. Then numbers 6 through 11. Numbers 12 through 20. 21 through 29. And 30 by itself. Poor 30. All right. So let's begin at the beginning with number 1.
So number 1 involves a jet landing. It gives us the model of the jet, which really has no bearing on the problem. It gives us the velocity as it comes in, 70 meters per second north, and it touches down and stops. So the final velocity is 0. It gives the acceleration as it comes to rest as 2 meters per second squared, but it's coming to rest. So if we're going to call the velocity positive, which I don't know why we wouldn't, if it's coming to rest, I'm going to call the acceleration negative because it's opposing the motion. So these are the things that I've told so far. Now I notice I put the acceleration in as positive. That is wrong. It is negative. And again, to repeat on that, it's negative because if I'm calling the initial velocity positive and it's slowing down, the acceleration acts against the velocity. And so if I'm calling the velocity positive and the acceleration is acting against it, I'm going to call it negative. Negative acceleration doesn't always mean slowing down. Slowing down just means that the acceleration is in the opposite direction of the velocity. If the velocity is north and it's slowing down, the acceleration is south. If the velocity is east and it's slowing down, the acceleration is west. If the velocity is down and it's slowing down, the acceleration is up. So if I have a negative velocity and I'm slowing down, the acceleration is against the velocity, so in that case, the acceleration would be positive. So don't automatically think that negative acceleration means slowing down. Slowing down is when the acceleration is in the opposite direction of the velocity. Speeding up is when the acceleration is in the same direction of the velocity. You can think of it as when you're speeding up, the acceleration is acting with you, but if you're slowing down, the acceleration is acting against you. So we wrote down our given information. The next thing we identify is what are they looking for? What's our unknown? So number 1 wants to know how far the jet went. One of the most common questions I get from students is what equation do I use? I don't know what equation to pick. Well, you pick your equation based on what you're given and what you're looking for. And then the second question is, well, I don't know what I'm given. And you can use the units to help you there. Notice that we have meters per second, that's going to be a velocity. We have meters per second squared, that's going to be an acceleration. It's another reason why knowing your units is so important. So I know V initial, V final, acceleration, and I'm looking for displacement. Notice that the V final, it didn't give 0 right in our face, but it does say brought to rest. Watch for that word rest. Starts from rest, V initial is 0. Comes to rest, V final is 0. So with VI, VF, and A, and looking for D, I'm going to use the third kinematics equation. VF squared is VI squared plus 2AD. As usual, I write the equation first. Second step is you put the numbers in with their units. You don't have to both list the givens with units and substitute with units, but I would do both if I were you. Some people really don't like substituting with units and would rather just list the givens with their units. That's okay, that's sufficient, but if I were you, I would do both, because if you mess up in one place, then you're not going to, and you get it in the other place, then you're not going to lose the points. Now, any intermediate math steps like this one don't technically have to be shown, but you can show them. It's not required. So I wrote out all of the math steps here just to kind of illustrate, but I usually don't. I leave that to you, because that's just the algebra of working through the problem. And you wind up, when you solve for D, since you're dividing a negative 4900 by negative 4, you get positive 1,225 meters, which the displacement is positive. Even though the plane is slowing down, its velocity is north and positive and still travels in that direction. So yeah, the displacement still is positive. If the plane were speeding up, if it were taking off, then that number would be larger. So I wrote 1,225 as what I actually got, and then I also write 1,200 because that's technically the right answer, because there are two significant figures in the original problem in terms of the information I'm given. So my answer should ideally have two significant figures. But again, when you're showing work, you're not being held to sig figs. So if you wrote 1225, you're okay. That's fine. Okay, next problem, next question. So here we have a scaled vector diagram. It says the scale is 1 centimeter to 0.5 meters per second squared. And they're asking us to draw the acceleration, which we know is negative 2 meters per second squared. Now, the original velocity was to the north, and acceleration is negative, so this vector is going to be to the south. So in terms of direction, we're going to have a southward vector because the acceleration is opposing the velocity. I'm doing this a little early in the morning. I'm not about to do the scale in my head, so I set up my ratio. Solve for x. So how many centimeters is to 2 meters per second squared if 1 centimeter is 0.5 meters per second squared? Cross multiply, and we're going to find that our vector is 4 centimeters long. I did that in my head, but I had to confirm it in my calculator because, like I said, I'm half asleep. I'm working on an iPad here with no real sense of scale, so I'm just going to sketch the vector in, but you're going to wind up with it starting at point P, and it's very important. When they tell you to start at point P, then start at point P. But starting at point P, you're going to have a downward vector of 4 centimeters long. Should look something like that. 4 centimeters long with a little bit of wiggle room, but I think you should be able to nail 4 centimeters. It doesn't say so in the problem, but usually questions like this are 2 points. 1 point to make sure that you draw the vector to the correct length, and another point to make sure it's in the right direction. There's no third point for the arrowhead, so if you miss the arrowhead, then you miss the point on direction. That's why I keep on beating that drum about remember your arrowheads. So number 3 is interesting. It gives us a table of times and speeds, but it says in the problem that the acceleration is constant. So I don't actually need 3 rows in this table. I really just need 2. I want to know how much time has passed, and I want to know what's the change in velocity, what's the delta V. So I can see that in 3 seconds, from 3 seconds to 6 seconds, in that time period, my V initial is 4 meters per second, and my V final is 8.5 meters per second. And the problem asks, what's the acceleration? So I have my givens, I have my unknown, I pick my equation. You can use the classic definition of acceleration, A equals delta V over t, or if I expand that out, A equals delta V over t is the version on the reference table, but I know that delta means final value minus initial value. Delta always means that in an equation. Or I could use Vf equals Vi plus At, the first kinematics equation, which mathematically is exactly the same as A equals delta V over t. I'm at the bottom of my slide here, so I'm going to have to start over on the right. I write my equation without substitution. I put my numbers in with their units. I get 1.5 meters per second squared, choice 3. Number 4, I'm not going to reread the problem. You could do that. So we have V initial 15 meters per second. We have V final is 21 meters per second. The time is 12 seconds, and it wants to know how far it goes. Got my givens, got my unknown. Based on the givens and unknown, I solve for how far. Now you can do this problem in 2 steps using equations on the reference table, or you can do it in 1 step. Let me show you the 2-step real quick. I have enough info here to either do d is vit plus 1f at squared or vf squared is vi squared plus 2ad. Only problem is I don't have a. It didn't give it to me, but I do have the initial velocity, the final velocity, and the time. So I could do a equals delta v over t, or a equals vf minus vi over t. I have enough information to solve for a. We call this a 2-step problem. If you're trying to solve for a problem like trying to solve for d, and then it turns out that you don't have a second thing, like A, you're going to have to do a second step to go and get it. Now, we don't actually have to do that here. We can do this in one step. But I wanted to show you a two-step problem that you would go off and do delta V over t, which is not that tough. Acceleration winds up being 0.5 meters per second squared, and you would throw that into the equation then, and then go and solve for d. But there's an equation, there's a version of v equals d over t that can solve this question in one step. Average v is d over t, but that's an average velocity. It's an average of the start and end values. So as the average, they add them up and divide by 2, and if we cross multiply and solve for d, d is vi plus vf over 2 times t. This version of v equals d over t is not on the reference tables. And you get 216 meters choice 3, which is exactly what you would have gotten if you did vit plus 1/2 at squared. But if you did that, you would have to go and solve for the acceleration. Again, not a big deal. Delta v over t. A is 0.5 meters per second squared. So you can go and solve for that A and then use it and do vit plus 1/2 at squared, but that's a two-step problem, and that's more work than you need. Also, the more work that you do, the greater the chance of the careless mistake. So why not bang it out in one shot? This boils down to personal choice. If you're terrible at memorizing things, like you're never going to remember that equation, then use what's on the reference table and do it in 2 steps. Otherwise, if you can remember this equation right here, that's why it's there. For problems just like this, you can answer it in 1 step. Alright, next question. Race car starting from rest. Again, there's that word rest. It doesn't say v initial or v final equals 0. It says rest. You have to remember that is a number. That's a piece of data. They give us the acceleration and tell us how far it will go, and they want to know the speed after it's traveled. So that's v final that it's looking for. I don't have the time. I don't need the time. Vf squared is vi squared plus 2ad. Sub with units. 0 squared is 0. And the answer is 1960 meters per second, choice 1. Wait a minute. First of all, that's ridic fast. Second of all, that's vf squared. Square root both sides. And I'm half joking about the ridic fast piece, because think about it. If it was 1960 meters per second, a football field is about 100 meters. So basically what you're saying is that in 1 second, the race car does 20 football fields? I don't even know if a rocket can do that. So no, not 1960. You get 44 meters per second. You don't get 44.3 because the acceleration is too sig figs. So the actual question thing is wrong. But whatever, nobody asked me. Choice 3, close enough. Next question. The classic dot diagram. They like to use these dot diagrams for representing motion. Notice that the first dot is 0 seconds, so that's when the timing started. And they call it a spark timer because there's a thing that makes sparks, and the electrical sparks literally burns a piece of paper, putting black circles on the tape, just so you know. So the first question, number 6, says, use a ruler to measure the distance during the first from 0 seconds to 0.3 seconds. And you're like, how the heck am I supposed to know that? Read the question. It says that a dot occurs every 0.1 seconds. So we start off at time 0, and the first dot after that is 0.1 seconds later, then 0.2, then 0.3. So we measure from the first dot, which is the 0 dot or the start dot, out to the 4th dot representing 0.3 seconds. And if you measure that out in the orange book, it comes out to 5 centimeters, which is the answer. I confirmed it. So it went 5 centimeters in that time. So 7 wants the acceleration, so let's write down what we know. We know that it starts from rest, so v final is 0. We know that the time is 0.3 seconds, and we now know from number 6 that in that 0.3 seconds, the cart went 5 centimeters. Now, you could leave the distance in centimeters and then solve for the acceleration in centimeters per second squared. I would just avoid the confusion. I would just convert centimeters to meters. You have to move the decimal place twice. Move the decimal place twice. So that's 0.05 meters. Now we're looking for the acceleration. We have VIT and D, and we want A. D is VIT plus 1/2 AD squared. I'm at the bottom of my slide, so I'm going to squeeze 0 times 0.3, that cancels. 0.3 squared is 0.09, and half of 0.09 is 0.045. Divide both sides by 0.045 to get A alone, and our acceleration is 1.1 meters per second squared. If you want to argue that the 5 centimeters is 1 sig fig, so that's actually 1 meter per second squared, I'm not going to fight you on that. But that's the answer. Let's move on. So 8 wants the average speed from 0 to 0.3 seconds. Would think that you would take the start speed and the end speed and average them, except we don't know the end speed. We can find it, but let's not. Instead, let's use the average speed equation, v equals d over t. Here's our givens. We know how far it went, 0.05 meters, or 5 centimeters. We found the acceleration to be 1.1 meters per second squared, and from 0 to 0.3 seconds, the time is 0.3 seconds. So v equals d over t. And there we have it. We have the equation shown, we have the substitution with units, and we have the answer with units. You technically could have put it in centimeters per second, just don't put 17 meters per second, because it's not 17 meters per second, it's 0.17 meters per second. Alright, number 9. So on another strip of paper, they want us to show a constant velocity. So a constant velocity would mean that the d over t is the same. For every interval of time, you're going to have the same position. So that means if I start with the first dot right there, as time goes on, it's going to be the same amount every time. We're going to have the same spacing every time. So it says at least 4 dots. I drew 5 dots to include the first one, but if it's constant velocity, you're going to have evenly spaced dots. Sometimes with this problem, instead of the tape timer, they have like a flashing light, or they might have an oil dripping from a car, but it's the same principle. I can also show you speeding up and slowing down. Speeding up would have dots close together, as if you were covering a small amount of distance over time, or going slowly, and then the spacing increases because your d over t is getting bigger. Your speed is getting bigger as you go. But if you slow down, then the spacing is going to get smaller because your speed is decreasing. That d over t is getting smaller, and so the spots are going to be closer together. Also be careful, they ask for at least 4 dots, so make sure that you draw at least 4 dots. Next, number 10. Given info, VI, VF, and D, they want A. Sub with units. Solve for x, or in this case, A. 2 meters per second squared. Next question. Pretty much the same as 10, different numbers. I will say one thing. They gave the directions of the velocities. They're both east. If one of them were west, like if V final were 8 meters per second west, I'd have to make that negative. So be careful when they do that, when they give you directions. It's the same directions here, so they're both positive. We're just going to do a delta V over T. Okay, next page, number 12. I'm obviously not hitting my goal of a minute per question, but there are more things to say about these problems. So we might have to break this into 2 videos again. Oh well, whatever. Alright, 12 and 13, design an experiment. We're trying to figure out acceleration of someone gliding down a slope. We have tape measures, traffic cones, and stopwatches. Okay, and we want to figure out acceleration. Well, let's think about the equations that we have that have acceleration in them, and then we can think about what measurements we're going to need in order to get there. So there are our formulas, and then honestly, we know the delta V over T and the VF is VI plus AT. Those are actually the same. So the variables we're talking about are time, displacement, and velocity. And the stopwatches can give us time, and then the combination of the tape measures and the traffic cones can give us displacement. The traffic cones that can mark the position, and the tape measures can mark off a certain displacement. I mean, if you had enough traffic cones and you took enough trials, you could get a simple velocity at the end. Like if you put traffic cones near each other and then did a average velocities, displacement over time at the very end. But I think there's a simpler way of doing this. Like if you had your hill, I mean that's quite a hill, but you get my point. And then set up 2 traffic cones with a known distance between them, and you started your rollerblader from rest, and then you timed them how long it would go from one cone to another, you could actually solve for the acceleration. So you could measure a known distance and mark it off with the cones, pick something reasonable, not too close together, but something you can actually time, like 10 meters. So yeah, and then once you have that distance, then you start a skater from rest. A friend times them as they roll through the 10 meters, starting from rest, of course, from the first cone, and then through from cone to cone, and then repeat it at least 3 times. Take at least 3 times, because this way, if you mistime it, you're really kind of timing this by eyeball, and probably the timer wants to be at the second cone, so you can line it up properly. They call that parallax error. But to at least 3 times and average the results. And then 13 wants to know what's the equations you should use to find the acceleration, which is pretty much part of the procedure. So you have d, you have t, and vi is 0 because you're starting from rest. And with d, t, and vi, the acceleration could be found with d is vit plus 1/2 at squared. Stick in the time, stick in the distance, put vi is 0, solve for a. Super, like, cut and dry, nothing fancy here. You got your givens, what's the acceleration, delta v over t, choice 1, next. 15, it says that the speed is decreasing, that means the acceleration and velocity are in the opposite direction. If the velocity is south, that must mean that the acceleration is north. Looking at the other choices, one choice says that the acceleration is 0. The acceleration is not 0 because the speed is changing. And then it says choice 4, the acceleration is constant but not 0. Maybe, but I don't actually know that. You could still be going south and slowing down and have a changing acceleration. But if you're going south and you're slowing down, the acceleration has to be north, or some component of it has to be north. So 15, for 15, choice 1 is the best choice. Okay, there are 30 problems in this set for kinematics, horizontal kinematics. And that's 1 through 15, and Educreations limits me out at 30 minutes, so I'm going to cut this one off here and then do 16 to 30 in another video. Hopefully that'll go faster, and I won't have to talk through so many of them, and it will go quicker. Alright, thanks.